Hey, I am Aditya and this is Environmental Chemistry Part 2. Particulate pollutants. Particulate pollutants are the minute solid particles or liquid droplets in the air. These are present in vehicle emissions, smoke particles from fires, dust particles, and ash from industries. Particulates in the atmosphere may be viable or non viable. The viable particulates example bacteria, fungi, molds, algae, etc. are minute living organisms that are dispersed in the atmosphere. Human beings are allergic to some of the fungi found in the air. They can also cause plant diseases. Non viable particulates may be classified according to their nature and size as follows. Smoke particulates consists of solid or mixture of solid and liquid particles formed during combustion of organic matter. Examples are cigarette smokes, smoke from burning of fossil fuel, garbage and dry leaves, oil smoke, etc. Dust is composed of fine solid particles over 1 micromillimeter in diameter produced during crushing, grinding, and attribution of solid materials. Sand from sandblasting, sawdust from woodworks, pulverized coal, cement, and fly ash from factories, dust storms, etc. are some typical examples of this type of particulate emission. Mists are produced by particles of spray liquids and by condensation of vapors in air. Examples are sulfuric acid mist and herbicides and insecticides that misses their targets and travel through air and form mists. Fumes are generally obtained by condensation of vapors during sublimation, distillation, boiling, and several other chemical reactions. Generally, organic solvents, metal and metallic oxides form fume particles. The effect of particulate pollutants are largely dependent on the particle size. Airborne particles such as dust fumes, mist, etc. are dangerous for human health. Particulate pollutants bigger than 5 microns are likely to lodge in nasal passage, whereas particles of about 10 micron enter into the lungs easily. Lead used to be a major air pollutant emitted by vehicles. Leaded petrol used to be the primary source of airborne lead emissions in Indian cities. This problem has now been overcome by the use of unleaded petrol in most of the Indian cities. Lead interferes with the development and maturation of red blood cells. Smog. The word smog is derived from the smoke and fog. This is the most common example of air pollution that occurs in many cities throughout the world. There are two types of smog. Classical smog occurs in cool, humid climate. It is a mixture of smoke, fog, and sulfur dioxide. Chemically, it is a reducing mixture, so it is called a reducing smog. Photochemical smog occurs in warm, dry, and sunny climate. The main components of photochemical smog result from the action of sunlight on unsaturated hydrocarbons and nitrogen oxides produced by automobiles and factories. Photochemical smog has high concentration of oxidizing agents and is therefore called as oxidizing smog. Formation of photochemical smog. When fossil fuels are burnt, a variety of pollutants are emitted into the Earth's troposphere. Two of the pollutants that are emitted are hydrocarbons and nitric oxide. When these pollutants build up to sufficiently high levels, a chain reaction occurs from their interaction with sunlight in which NO is converted into nitrogen dioxide, NO2. This NO2 in turn absorbs energy from sunlight and breaks up into nitric oxide and free oxygen atom. Oxygen atoms are very reactive and combine with O2 in the air to produce ozone. The ozone thus formed rapidly reacts with NO in the gaseous form to regenerate NO2. NO2 is a brown gas and at sufficiently high levels can contribute to haze. Ozone is a toxic gas and both NO2 and O3 are strong oxidizing agents and can react with unburned hydrocarbons in the polluted air to produce chemicals such as formaldehyde, acrolein, or peroxyacetyl nitrate (PAN). Effects of photochemical smog. The common components of photochemical smog are ozone, nitric oxide, acrolein, formaldehyde, and peroxyacetyl nitrate. Photochemical smog causes serious health problems. Both ozone and PAN can act as powerful eye irritants. Ozone and nitric oxide irritate the nose and throat, and their high concentration causes headache, chest pain, dryness of the throat, cough, and difficulty in breathing. Photochemical smog leads to the cracking of rubber and extensive damage to the plant life. It also causes corrosion of metals, stones, building materials, rubber, and painted surfaces. How can photochemical smog be controlled? Many techniques are used to control or reduce the formation of photochemical smog. If we control the primary precursors of photochemical smog, such as NO2 and hydrocarbons, the secondary precursors such as ozone and PAN, the photochemical smog will automatically be reduced. Usually, catalytic converters are used in the automobiles which prevent the release of nitrogen oxide and hydrocarbons to the atmosphere. Certain plants, example Pinus, Juniperus, Quercus, Pyrus, and Vitis can metabolize nitrogen oxide and therefore their plantation could help in this matter. Section 14.2.2 Stratospheric pollution, formation and breakdown of ozone. The upper stratosphere consists of considerable amount of ozone, O3, which protects us from harmful UV radiations with wavelengths about 255 nanometer coming from sun. These radiations cause skin cancer, melanoma in humans. Therefore, it is important to maintain the ozone shield. Ozone in the stratosphere is a product of UV radiations acting on dioxygen molecules. The UV radiations split the molecular oxygen into free oxygen atoms. These oxygen atoms combine with the molecular oxygen to form ozone. Ozone is thermodynamically unstable and decomposes to molecular oxygen. Thus, a dynamic equilibrium exists between the production and decomposition of ozone molecules. In recent years, there have been reports of depletion of this protective ozone layer because of the presence of certain chemicals in the stratosphere. The main reason of ozone layer depletion is believed to be the release of chlorofluorocarbon compounds, also known as freons. These compounds are non-reactive, non-flammable, non-toxic organic molecules and therefore used in refrigerators, air conditioners, in the production of plastic foam, and by the electronic industry for cleaning computer parts, etc. Once CFCs are released into the atmosphere, they mix with the normal atmospheric gases and eventually reach the stratosphere. In stratosphere, they get broken down by powerful UV radiations, releasing chlorine-free radicals. CF2Cl2 gaseous in the presence of UV radiations breaks down into chlorine-free radical and CF2Cl free radical. The chlorine radical then reacts with stratospheric ozone to form chlorine monoxide radicals and molecular oxygen. Chlorine radical combines with ozone molecule to form ClO radical gaseous plus O2 gas. Reaction of chlorine monoxide radical with atmospheric oxygen produces more chlorine radicals. Chlorine radical in the gaseous form combines with atomic oxygen to give chlorine free radical and oxygen gas. The chlorine radicals are continuously regenerated and cause the breakdown of ozone. The CFCs are transporting agents for continuously generating chlorine radicals into the stratosphere and damaging the ozone layer. The ozone hole. In 1980s, atmospheric scientists working in the Antarctica reported about depletion of the ozone layer commonly known as the ozone hole over the South Pole. It was found that the unique set of conditions were responsible for ozone hole. In summer season, nitrogen dioxide and methane react with chlorine monoxide and chlorine atoms, forming chlorine sinks, preventing much ozone depletion. Whereas in winter, special type of clouds called polar stratospheric clouds are formed over Antarctica. These polar stratospheric clouds provide surface on which chlorine nitrate formed gets hydrolyzed to form hypochlorous acid. It also reacts with hydrogen chloride produced to give molecular chlorine. When sunlight returns to the Antarctica in the spring, the sun's warmth breaks up the clouds and HOCl and Cl2 are photolyzed by the sunlight as given in these reactions. HOCl gaseous in the presence of the sunlight gives OH free radical and Cl free radical. Cl2 gas in the presence of light also forms 2 Cl free radicals. The chlorine radicals thus formed initiate the chain reaction for ozone depletion as described earlier. Effects of depletion of ozone layer. With the depletion of ozone layer, more UV radiation filters into troposphere. UV radiations lead to aging of skin, cataract, sunburn, skin cancer, killing of many phytoplanktons, damage of fish productivity, etc. It has also been reported that plant proteins gets easily affected by UV radiations which lead to the harmful mutation of cells. It also increases the evaporation of surface water through the stomata of leaves and decreases the moisture content of the soil. Increase in the UV radiations damage paints and fibers, causing them to fade fast.